Good morning, friends. Already we discussed about interference and diffraction, right? Now the last topic of the diffraction, the validity of ray optics, or what is the importance of the Fresnel distance. So first we have to know that what is the Fresnel distance. Fresnel distance, that means in diffraction phenomena, whatever the distance between the slit and screen, right? Capital D. How that is known as the Fresnel distance. Here we are going to discuss this thing and what is the importance of that. Now for that purpose here, in phenomena of the diffraction, like this slit, there is the slit. Slit is illuminated by the light. So each particle of the wavefront and also the slit behave as a secondary source and produce the secondary spherical waves. These waves superpose on each other and produce the interference pattern. That means the bright and dark fringes on the screen. That is the screen. That is the slit. The width of a slit is A. Wavelength of a light used is lambda. And that is the capital distance. That is the distance capital D. What's happened? If the distance is small, therefore the spreading of the diffracted beam of light is less. If we keep the screen at large distance, what's happened? The spreading is more, like this. If the screen is here, so spreading of the central maxima is this, and here the spreading of the central maxima is this. So the spreading of what are the images or the interference fringes obtained on the screen, that is depends on the distance between the slit and screen. So that is the importance of the Fresnel diffraction. Now one more thing, in our daily life we know that in a room, suppose there is the door, side of the door. Whatever the light is inside the room, one bulb is illuminated. So the rays of the light coming from the bulb passing through this area of the door. So as a result, on the floor, here we saw the shadow is like this. Shadow of the waves are like this. So actually here the size of the door is same at top and bottom, but at the bottom here the spreading of the diffracted light, here the edge of this door is act as a slit, therefore whatever the light is incident on the edge of a door, so there is the diffracted, So as we go away from the door, so spreading of this diffracted light is going to increase, So that is the Fresnel distance. Okay. Here we are going to discuss this thing. If the aperture of the size A is illuminated by the parallel beam of light, that means there is the aperture of a slit having the size is A, that is the illuminated by the parallel beam of light. So due to the incidence of a parallel beam of a light on a slit of the aperture, so diffraction phenomena take place, therefore the light is diffracted at angle theta. And angular width is theta is equal to lambda upon A. Already we discussed in central maxima, first minima and secondary maxima. So theta is equal to lambda upon A. Due to diffraction in traveling distance D, that means after the diffraction phenomena, if the diffracted wave travels the distance D, so angular distance or the angular width is D into theta. Here we consider this distance as a Z. Therefore, due to diffraction in traveling distance Z, the diffracted beam acquires the angular width is equal to Z into theta. Z is the distance of the slit and screen. Okay. Therefore, Z into value of theta is equal to lambda upon A. Therefore, Z lambda upon A. Now, due to diffraction, the spreading beam of light is equal to the side of aperture. In phenomena of diffraction, how the light is spread, that is depends on the side of a aperture and is equal to A. Therefore, A is equal to ZA upon lambda. That means the Z into theta is our aperture side of aperture. Therefore, Z lambda upon A is equal to A. Take this side. Therefore, A is equal to Z lambda. Z lambda upon A. Therefore, Z is equal to A square upon lambda. This quantity Z is known as the Fresnel distance, that is denoted by ZF. That is denoted by ZF. Capital Z, suffix capital F. Therefore, ZF is equal to A square upon lambda. Therefore, ZF is equal to A square upon lambda. Again, if the side of a person A is illuminated by the parallel beam of light. So after the diffraction, the diffracted beam is seen at angle theta, or this light is diffracted at angle theta. Then the angular width is theta is equal to lambda upon A. We accept this equation directly from already a discussion for central maxima, first minima and secondary maxima. Now, due to diffraction, in traveling distance Z, the diffracted beam acquires the angular width is equal to Z into theta. Is equal to Z, theta is equal to lambda upon A, therefore Z lambda upon A. Now, due to diffraction phenomena, the spreading of the beam of light is equal to aperture side of aperture A. Therefore, A is equal to Z lambda upon A. Therefore, Z is equal to A square upon lambda. This quantity Z is known as Fresnel distance, that is denoted by ZF. Therefore, ZF is equal to A square upon lambda. Now listen, this equation shows that if the distance Z is less than Fresnel distance ZF, therefore the spreading of beam due to diffraction is smaller than the side of a beam. The side of a beam. If this distance, that means the distance between the slit and screen, is less than, this distance is Z, Z is less than ZF. At that time, whatever the spreading of a beam of light is smaller than the side of a beam. So that is the importance of the Fresnel diffraction. So in our case, this equation is important because the one illustration, I think the 10.6 is given. And sometimes here the objective question is need and also with scale asked from this equation from Fresnel distance. Here the size of a slit or the width of a slit is given and wavelength of a light used in diffraction phenomena are given. So find the Fresnel distance. Right? So this type of a question is asked for objective or also 2 marks numerical. Okay. So there is the Fresnel distance. Okay, now, after the phenomena of interference and diffraction, the third phenomena of light is polarization. Now, what is the polarization and how the polarization is take place? First, we have to discuss about that. What is the wave? Already we discussed about the definition of a wave. The disturbance propagating in a medium is known as the wave. Right? Now here we are going to discuss in terms of the polarization. For that purpose, we also know the different waves. Now, if the one string is tied, one end of the string is tied with a fixed support and second is held by our hand. Third is in our hand. And now this long string is kept horizontal. If her hand is moved up and down periodically, so what's happened? As we periodically moves up and down this end of a wave, so what's happened? The disturbance produced in a string. The disturbance produced in a string, that means the waves are generated and these waves are propagating in horizontal direction. Either the positive x direction and also negative x direction. What are the waves generated here? This way. So there is the incident wave. This incident wave is reflected from the rigid support already we learned in 11th standard in waves chapter. Incident and reflected wave. So here, what are the shape of the disturbance produced in a string is shown in the figure. At time t and at time t plus delta t. That is at time t, that is at time t plus delta t. Now listen, the distance between the two consecutive cracks is known as the wavelength. That is the wavelength. Here, this disturbance is propagating in positive x direction, that means the wave is generated and propagating in positive x direction. Therefore, the displacement changes with time, and this displacement occurs along the y direction. Here the string is along the x direction and displacement of all the point of the string occurs in y direction, that is the y-x. Therefore, the equation of the displacement is represented by yxt is equal to a sine kx minus omega t. Actually, there is the wave equation. This wave is propagating in one-dimensional harmonic progressive wave. Here, the shape or the oscillation of this wave is perpendicular to the direction of propagation. Therefore, this type of the wave is known as the transverse wave. So, in the beginning of the polarization, first we discussed about what is the polarized, what is the unpolarized wave, and before this, what is the linearly polarized wave or the plane polarized wave. For that purpose, the basic is that explain linearly polarized wave and define it. For that purpose, we consider a long string with one end fixed and other end is kept horizontally. When the free end of the string is moved up and down periodically, the wave generates in it propagating along the x direction. We are going to add on this thing. Consider a string, consider a long string with one end fixed and other kept horizontal. Kept horizontal. Then a free end of a string moves up and down. A wave generates in it in a string, propagating in x direction as shown in here. Because at time t and t plus delta t, at time t and t plus delta t, represents the displacement of the particle of a string. The wave propagating in x direction and the change in displacement with time show one in figure. If the displacement occurs in y direction, then its equation is y xt is equal to a sin kx minus omega t. Is the wave equation. Is the equation of wave. Here A is equal to amplitude of a wave. Omega is equal to angular frequency. Is equal to 2 pi f. K is equal to wave vector. Is equal to 2 pi upon lambda. And lambda is equal to 2 pi upon k. 2 pi upon k is the wavelength. Is the wavelength. So thus, during the wave, whatever the displacement of the particle of the string occurs, that means the disturbance occurs in a string, and due to this disturbance, here the particle of the string will oscillate along the y direction. So, the equation of the displacement is represented by this equation, y is equal to a sin kx minus omega t. Here the terms are a is equal to amplitude of wave, omega is equal to angular frequency, and k is the wave vector. Already about this equation we learned in 11th standard. Now, which type of the wave represented by this equation is known. Here we discuss. Now here the figure of this displacement occurs in a long string is like this way. Here the one end of the string is tied with a fixed support. So that is the one. There is the string, there is the tie. Now, what are the waves are generated in this string due to the moving of free end is moving up and down. So waves are generated like this manner. Waves are generated like to this manner. That is the position at time t is equal to 0. Time t is equal to 0. Now listen of the waves generated in the string at time initial time t and t plus delta t. Therefore, there is the fixed support. Here, whatever the disturbance produced in a string is propagated in positive x direction. Positive x direction. There is the situation at time t. Now, After some interval of time, this wave occurs like this way. That means this disturbance is traveling the distance in x direction. So the position of the disturbance after the t plus delta t time is shown here. There is the position at t plus delta t time. This distance is known as distance between the two crests. That is known as the wavelength lambda. There is the wavelength lambda. Here, this fluid is moving up and down periodically. Moves up and down periodically. There is a y direction, x and time. So here the figure shows the displacement of the particle of a string at time t and at position x and y. Now it's shown in the figure from the figure. The displacement of particle of a string is perpendicular to the direction of propagation of a wave. Therefore, this wave is known as the transverse wave. Here, displacement of particles of a string are global to the direction of propagation of a wave. So, such wave is known as transverse wave. Therefore, what are the waves generated in the string are known as the transverse wave. Okay. The displacement of each point of a wave is along the straight line, that means the y direction only. Therefore, that is known as the y polarized wave. The displacement is in y direction. So it is called y polarized wave. Y polarized wave. Because here the displacement occurs only in y direction. Now, linearly polarized wave. The displacement of each point of a wave or each point of a string are moving along the straight line. That each point of a string moves in a straight line. That means y direction only. So it is known as linearly polarized wave. Linearly polarized wave. And last definition is the plane polarized wave. Here the string is kept in xy plane. That is in xy plane. Now the string is in xy plane. Thus, such wave is known as plane polarized wave. So that is the definition of the different of the wave. Actually here the wave produced in a string are also transverse wave, because here the oscillation or the displacement of the particle occurs perpendicular to the direction of propagation of the wave. Therefore that is known as the transverse wave. Now here the displacement of a particle is along the y direction, therefore only the y polarized wave. Right? Okay. Now in third way, the displacement of each point of a string moves up and down in straight line. Straight line is y direction, so that is also known as the linearly polarized wave. Now next is the string is kept in xy plane. Therefore, what are the waves generated is this wave is known as the plane polarized, because that is the disturbance occurs along the y direction but propagating in x direction. So only keep in mind this for definition, that is important. After that, if the string is kept in xz plane, what's happened? Instead of the y. So here the displacement of the particle of the string occurs along the z direction. Occurs along the z direction. So that is known also the plane polarized, transverse and linearly polarized wave. But here the equation is represented by, instead of the y, here the z. Z is equal to xt is equal to a sine kx minus omega t. Clear? Okay, now just we discuss about the linearly polarized wave and also the plane polarized wave. Here we consider the propagation of a wave along the x direction and displacement of the particle at the point of a string along the y direction. Right? Now, as we consider, if the displacement in a string are in xz plane, or the string is kept in xz plane, therefore the wave generated, that is known as the z polarized wave. If the string is in xz plane, the wave generated in a string are z polarized wave. And its equation is zxt is equal to, equation is same as this, sine kx minus omega. It is also linearly polarized wave. Linearly polarized wave and also transverse wave. Because here also the wave is propagating in x direction, but the oscillation takes place along the z direction, along the z direction. Therefore, there is also a transverse wave, and here the displacement of a particle of a string occurs only along the z direction. That means on a straight line. Therefore, there is the linearly polarized wave. Okay. So that is the beginning of the polarization. First, here the next definition is what is the unpolarized light and polarized light. So define. Next question is that define unpolarized and polarized light. Okay, now we know that the sunlight or the light is the electromagnetic waves. What are the light coming from the sun or any tube light or the bulb? This light is the unpolarized light because there is the electromagnetic waves. Its speed in vacuum is same as the speed of light in electromagnetic waves in vacuum. Therefore, light is known as the electromagnetic wave. Its speed is 3 into 10 is to 8 meter per second. Okay, light is an electromagnetic wave. Light is an electromagnetic wave. In the light, the oscillation of or the displacement or oscillation of electric field E or the electric vector is in all direction normal to the direction of propagation of a wave. Thus, it is known as unpolarized light. Unpolarized light. The schematic representation of A is shown in figure. Now listen, first the light is electromagnetic waves, therefore the electric field vector oscillates in all directions. This direction is perpendicular to the propagation of a wave. Right? Therefore the light is known as the unpolarized light. Now here we discuss about the electromagnetic waves. There is the X direction, there is the Y direction, and there is the Z direction. Now what's happened? There is the electromagnetic waves are. The electric field vector are oscillate like this way. X is the propagation direction of propagation. Now electric field vector are oscillate along the Y direction or in a straight line Y direction. While the magnetic field component are oscillate along the Z direction like this way. Therefore, the electric field and magnetic field both are perpendicular to each other. Here we are discussing about only the electric field vector oscillate along the Y direction that is perpendicular to the X. There is not fixed along the Y direction. There is also any direction, this way, this way, this way. So there is perpendicular to the direction of propagation of wave. Therefore, there is known as the unpolarized light. And schematically, symbolically, there is the shown like this way. The electric field component of the vector are oscillate in all directions like this. And there is also represented by, here the light is this, propagating this direction. So here the two direction oscillation are shown. This by dot and also by the vector, this way. So that is for the symbolically representation of unpolarized light. So here this arrow represents the oscillation of electric field vector vertically upward downward, while dorsal represents the oscillation of electric field vector inside and outside this way. So both symbol for the unpolarized light. After that, the polarized light. That is now next is the polarized light. Now in polarized light only the oscillation of or the displacement of E vector are coplanar and parallel to each other. That means only in one direction. Polarized light. The light in which displacement of E are coplanar and parallel to each other. Parallel to each other. And perpendicular to the direction of propagation. Direction of propagation is known as polarized light. As shown in figure. As shown in figure. So polarized light is shown like this manner. Either the oscillation of the electric field vector this way, that is the up or down, or inside and outside. Inside and outside. This way. So here the electric field it oscillates inside outside. Here the electric field it oscillates up and down, up and down. So there is the polarized light schematically represented. There is the unpolarized light. Clear this?